Good evening. My name is Fatma Yücel. I'm a researcher at the TU Berlin with a focus on pressure gain combustion, mainly the shockless explosion combustion. And today I'm going to present my recent work on which I have been working in cooperation with my co-authors Fabian Habicht, Miles Bohun, and Christian Oliver Paschereit. This work contains experimental investigation on the autoignition of a stratified fuel-air mixture in a continuous airflow, in order to achieve a pressure rise similar to a constant volume combustion. Pressure gain combustion is a promising concept for improving performance and efficiency of a conventional gas turbine cycle. The principle can be applied to both power generation and propulsion. Nowadays, conventional gas turbines are based on the Brayton cycle, in which the mixture is burned at constant pressure conditions. Using constant volume instead of a constant pressure combustion leads to a significant increase in thermal efficiency. Different approaches for realizing a pressure gain combustion rather than an ideal constant volume combustion were proposed, developed, and investigated. Existing concepts are based on an unsteady process in which the gas expansion due to heat release is constrained, causing a rise in pressure which allows for an increased work extraction. Detonation-based concepts such as pulse detonation and flotation detonation combustors take advantage of a propagating detonation wave that burns a reactive mixture quasi-instantaneously such that it has no time to expand, leading to a sharp increase in pressure. However, sharp pressure peaks can harm mechanical components and are undesirable. Pulse jets, whereas, make use of a geometric confinement that limits the gas expansion. Since the utilized deflagration wave is relatively slow, a gradual and low rise in pressure is achieved. The shockless explosion combustor is a new approach and aims for a homogeneous autoignition, which leads to an aerodynamic confinement during the combustion process. By this, a gradual increase in pressure is achieved, higher compared to that of a pulse jet. The SEC is based on a periodic combustion process. At first, the combustor is filled with an axially stratified fuel-air mixture. This stratification is an essential part of the SEC process. It has to be precisely realized in order to achieve a homogeneous autoignition. After a certain delay time, the injected mixture undergoes a homogeneous autoignition, leading to a gradual pressure rise. A pressure wave is initiated at the contact surface of the burnt gas and the previously injected air buffer, which travels downstream the combustor. The pressure wave is reflected at the acoustically open end of the combustor and travels upstream as an expansion wave. Once the expansion wave reaches the tube inlet, the pressure inside the combustor falls below the supply pressure, which supports the refilling process. The initial inflow is used for purging and separating the reactant mixture from the next cycle from the hot exhaust gases by an air buffer. Subsequently, fuel is added to the airflow, resulting in a stratified fuel-air mixture to restart the cycle. As mentioned earlier, the fuel stratification is a vital part of achieving a homogeneous autoignition. The fuel is injected at the combustor inlet by 10 high-speed solenoid valves. This causes a variation in spatial distribution of the residence time throughout the injection period. In order to achieve a homogeneous autoignition, this variation in residence time needs to be compensated. For this, the ignition delay time has to be precisely adjusted by varying the local equivalence ratio such that a constant distribution of the ignition time throughout the combustor is achieved. In experiments, however, achieving a perfect homogeneous autoignition is not feasible. Instead, it is aimed for a quasi-homogeneous autoignition initiated by multiple ignition sources. This type of ignition has been successfully implemented in previous experiments. The degree of homogeneity of an autoignition is highly dependent on the applied injection procedure and linked to the existing flow conditions. Therefore, it is important to ensure that the injection strategy is capable of injecting a predefined fuel profile which stays largely preserved until ignition occurs. A test rig is designed to allowing for the investigation of the correlation between autoignition and fuel distribution under atmospheric pressure and elevated temperature conditions. The test rig is composed of several sections including reactant injection, convection, combustor, and exhaust section. A preheater is used to rise the air temperature to 1023 Kelvin. Downstream the preheater, the airflow is forced through a restriction in order to prevent backflow of hot gases subsequent to ignition. 10 high-speed solenoid valves are used to inject a defined fuel trajectory. Pressure sensors and ionization probes are installed to measure the pressure rise subsequent to ignition and the ignition time respectively. After injection, the fuel package convects downstream the convection tube until ignition occurs. Preliminary experiments are conducted to validate the control of the injection geometry to achieve a defined mixture profile within a desired time frame. For this, tunable diode laser absorption spectroscopy is applied. This technique has been previously applied for time-resolved fuel concentration measurements for similar configurations. Methane is used as a tracer fuel to match the absorption features of the available laser. While this prevents quantifying the exact local equivalence ratio for the reacting DME cases, it does allow for a qualitative measure of the reproducibility and accuracy of the injection scheme. To ensure equal conditions, the bulk velocity and thus the convection time is kept constant. 3 example fuel trajectories are injected into a convecting airflow 150 times with a frequency of 5 Hz. The cycle average fuel concentration reveals a clear smoothing effect, especially in the regions of high gradient. This can be attributed to turbulent diffusion and shear layer effects. However, a distinct difference is visible in the measured fuel concentration profiles, indicating that the applied injection strategy is suitable for injecting a defined fuel profile which stays largely preserved throughout the measurement area. The 3 introduced injection profiles are applied under reacting conditions using DME as fuel. The pressure subsequent to ignition is measured via 5 pressure sensors which are flush-mounted into the combustor. Ionization probes are used to measure the ignition time at 8 axial positions inside the combustor, allowing for the evaluation of the homogeneity of the ignition front. When correlating the maximum obtained pressure amplitude delta P max and the degree of homogeneity, which is characterized by the delay of ignition and pressure rise, a clear increase in pressure is visible with an increase in ignition homogeneity. There's quite a lot of cycle-to-cycle variance for each specific fuel profile. However, a notable shift towards higher pressure amplitudes for an increased homogeneity is visible. When comparing the 3 injection profiles, the lambda-shaped curve tends towards a more homogeneous ignition, while the V-shaped profile is less homogeneous. The square-shaped profile falls generally in between. A higher homogeneity indicates a higher number of quasi-simultaneous detection of ignition. 2 types of ignitions are identified, broadly classified as Regime 1 and Regime 2, showing distinct differences in ignition characteristics. Proper orthogonal decomposition is applied for 50 cycles for both regions. The dominant PID modes of the pressure histories of sensor P1 and P5 are visualized representing a cycle average pressure signal. The pressure traces reveal pressure rise subsequent to the ignition event. In both cases, the area of high pressure is followed by an area of low pressure due to the reflected pressure wave that travels upstream the combustor as an expansion wave. However, when comparing both pressure regimes, a notable difference in amplitude is visible. Additionally, the pressure rise detected by the respective sensors is simultaneous for Regime 1. In case of Regime 2, the pressure traces reveal a rather propagating pressure wave. To further explore the ignition process, a setup with optical axis is used to measure the OH star intensity and the pressure simultaneously. The optical accessible section is composed of a series of 4 quartz tubes supported by flanges fitted with 1 pressure sensor each. An optical bandpass filter, an intensifier, and a high-speed camera are used to detect the reaction zones by light emission of OH star intensity. The temporal evolution of the flame fronts is visualized by XT diagrams. Every time step in the XT diagram represents an average OH star intensity for all pixels of a single image at the respective axial position. The vertical shadows in the image correspond to the combustor supports, and the pressure traces at these locations are overlaid. In this figure, two different cycles for the lambda-shaped curve and one for the V-shaped curve are visualized. These three cycles represent various visible ignition events observed for many cycles. A uniform, highly distributed ignition front with multiple points of ignition is visible in the first example. Compared to the other examples, this region after ignition shows the highest OH star intensity. Furthermore, the largest amplitude and pressure signals are observed. The distributed ignition results in an aerodynamic confinement which serves to increase the pressure more than in the other examples. As the products expand, the pressure falls and reaches a local minimum. The ignition obtained in the second example is less uniform and instead propagates primarily from a single ignition point. The calculated propagation velocities reveal a nearly constant velocity upstream and downstream direction when accounting for the bulk velocity. Thus, in the second case, a propagating turbulent flame is observed rather than an autoignition front. The last example shows the distribution of OH star intensity for a measurement with a V-shaped curve. Here, the first ignition point occurs close to the image frame. Compared to the first two examples, the ignition occurs much more downstream in the combustor. Subsequently, a deflagration propagates upstream in the combustor. Simultaneously, a weaker pressure wave can be seen in the pressure histories traveling at the speed of sound. A second deflagration is then propagating downstream in the combustor, indicating a second autoignition event has occurred further upstream. Presumably, these two ignition events correspond to the local maxima in the fuel injection profile. In this case, the reduced aerodynamic confinement due to multiple separated ignition points results in the smallest increase in pressure. To conclude this presentation, I will give a brief summary. A novel test rig was presented equipped with a controllable reactant injection system, which was designed to deliver a prescribed charge of autoignitable mixture. As a next step, the reproducibility of three arbitrarily defined profiles was demonstrated using a time-resolved line-of-sight measurement technique. These profiles were subsequently used to investigate the correlation of pressure rise and ignition homogeneity. Observing the ignition processes for different ignition regimes, broadly classified as regime 1 and 2, supported the conclusion that a distributed uniform autoignition event results in a greater overall pressure rise. An optical setup was used to obtain the temporal evolution of the ignition event by OH star light emission. The results support the pressure rise due to aerodynamic confinement. These phenomena are repeatable and measurable, which is an important requirement for the use of a shockless explosion combustor as a pressure gain combustion device. Thank you for your attention.